Swayam Prabha. Digital India. Educated India.
So having given you an overview of how to tackle stability problems, we are now in a position to address what happens to a thin jet as it basically falls down. When a thin jet is falling down, we've already seen images. If you think of this as a tap, then as the jet descends down, it thins down gradually, and then eventually it breaks up into droplets. This problem was first tackled by Plato, where he studied the stability of the jet and showed that if you introduce undulations on a jet, then the overall surface area decreases, and so you reduce the surface area and hence the surface energy, and it becomes a favorable configuration to move to from a straight undulated filament to an undulated filament. Rayleigh, on the other hand, basically studied this problem for a stationary filament. Now what I want to do in this lecture is to revisit the problem of Rayleigh and do it the way Rayleigh has essentially done, which is to look at the stability analysis of a filament. The problem of that I'm showing you here on the screen is actually a spatial stability analysis, and this was also carried out in 1972 by Keller et al. In a paper published in Physics of Fluids. So let's revisit the problem that Rayleigh did for a filament. But let me first explain how do we get a filament. There are several ways to do it. One is to say, here's a filament and I want to do the stability analysis because this is the easier configuration to study. But we can also see that there is some connection between a spatial analysis and a temporal analysis. I won't go into those details in the course, but I will give you some insight of how we can think of how a filament sort of emerges in this analysis. So if we look at this thinning filament, let's say I look at certain sections of this filament, right? So if I look at the first section, what we have is we have a filament. I'm drawing a bigger version of the same filament, and if the filament is reducing gradually, then what I have in that little section is I almost have something like a plug flow. The reason I have a plug flow is because in this problem we are assuming that the surrounding gas is basically passive and it has no viscosity. Therefore, the tangent stress as boundary condition simply reduces to the statement that the shear stress at the interface is 0, and at leading order you get a plug flow. Now if you were to take the same filament at much further down, then it becomes even more straighter and you have a higher velocity because the jet is thinner. Now if you were to observe this problem, it's a spatial stability analysis. So one way to do this experiment, if you were to set up an experiment, is you basically put a camera and observe the entire jet. So if you use a fixed camera, what you get is a spatial stability. One sees a spatial stability. Okay. But you can also do one more thing, which is to actually have a camera that is moving. That is moving with the local velocity. Okay. This is easier said than done, but it's a thought experiment. If you do this, then you have a moving camera. What you now have is, you see you're traveling with the flow, and what you see is a temporal instability. I'm making several gross simplifications here. An alternate example would be to think about what a person would see when you stand at the beach. You see the waves moving. So that's basically like the fixed camera experiment, and you see things basically changing in space. Another experiment would be where you're traveling with the wave. Let's say you're a surfer on the wave, and what you see is the wave for you remains stationary because you're on the wave. You don't see the wave moving. Okay. But if the wave is, let's say, increasing in amplitude as it reaches approaches the beach, the wave amplitude increases, and therefore, if you're a surfer on such a wave, you would actually go up, and you would perceive it as a temporal growth, a growth which is changing in time. Okay. So that's the moving camera experiment. Okay. So, if you move with the flow, hopefully I've convinced you that you can think of it as a filament where you see temporal growth. So that's the first part of the puzzle. There is some meaning to study a temporal analysis. Okay. Now, the next thing is, if the jet is not varying too rapidly, then for large portions of the jet, you can assume that the radius of the jet is nearly constant. And if the radius of the jet is nearly constant, the velocity is also constant. Because if you remember, in the shape of the jet analysis, we found that the radius of the jet and the velocity of the jet are directly related, and the relation was also obtained just from mass balance, right? So, if we assume that the jet is varying gently, for a gently varying jet, what you can think of it is, we can approximate the jet as approximate the jet to have a constant radius. So now what we have is, we have a filament whose radius is constant. This could still be a falling jet. If it's a falling jet, all that we need to do is to make it into a stationary filament. Okay. The falling filament with constant velocity can be made into stationary filament. Using what is known as a Galilean transformation. If you use a Galilean transformation, you basically you can subtract out that constant velocity, and what you have is a stationary filament, a filament which is not moving. So now this brings us to the next step, which is stability of a stationary filament. right? Let me first draw the filament again. So we can think of a filament of radius r naught, and the pressure inside is P naught. Now, the first step in the stability analysis, what are the key steps in the stability analysis? We take a base state. So this is our base state. Base state or base flow, but even though it's a stationary filament, we have our base state, and on the base state we apply some perturbations, and then we linearize the system of equations, and after we linearize them, we can use the method of normal modes, and we can reduce them to a bunch of ordinary differential equations and get the dispersion relation and so on. The first step is to introduce a perturbation, but because this is a filament, I can actually apply the perturbations to the surface of the filament. Okay, it's easy to think of perturbations to the filament boundary rather than to the velocity. Okay, so let's look at the filament boundary. So I can actually think of two kinds of perturbations. I can think of a perturbation. Let me first draw the axis here. I can think of a perturbation which would, I'll show the unperturbed filament in red. This is an exaggerated perturbation. I can think of a perturbation which would make the filament become like this. Okay. So in other words, you're squishing the jet at a few places, and as a consequence, the jet has to bulge out at a few other consequent places. Okay. This kind of a mode is called the varicose mode. Okay. Now you can have another kind of mode which takes this jet and again, this is a I'm drawing the perturbation of very large amplitude. So don't think that it's a violation of the linear analysis that we're going to do subsequently. This is only for illustration. So I could actually have a perturbation this way as well. Okay. So now I have two kinds of perturbations. One is the varicose perturbation, or I could have a sinuous perturbation. Okay. Just like how a snake would move. Okay. So sinuous perturbation both are possible. Now we can actually do a stability analysis with both these modes included. Okay. But I would rather not do that. I know that varicose mode is the most unstable mode from experiments, and therefore for this analysis I'm only going to do the varicose mode. What distinguishes one mode from the other mode is not only the surface, the shape of the jet or the filament, but also the velocity field inside. Okay. We will see this when we apply boundary conditions on the axis. Okay. So I'm going to assume that we are only going to do the varicose mode. Okay. The reason for this is because we know from experience unstable, to keep the analysis simple and clear, we will be studying only the varicose mode. Okay. But in general, you could set up an arbitrary perturbation which has a combination of sinuous and varicose modes and see how they evolve. What you will find is the sinuous mode will decay if you have viscosity. If you do it for an inviscid jet, the sinuous mode basically would just have neutral stability, which means that it will just oscillate and it will not give you any growth rate, whereas the varicose mode becomes unstable. Okay. We'll do the varicose mode in this analysis. So how do we basically set up the perturbation? Okay, so if I think about this at any arbitrary location, I can say that the radius is basically has it's deviating from its constant value, right? For this, I need to first define the coordinate system. What is my coordinate system? I will define my coordinate system in the original undisturbed base state so that my drawings are clear. So we basically have somewhere here, so this is an infinite filament now for me. And in this infinite filament, I'm also neglecting gravity because I want to show that what is the role of surface tension. Okay. So up and down has no meaning when you have gravity. In fact, you'll find in a variety of books and other sources that you'll find this analysis where the filament is shown horizontally. Okay, so it makes no difference. So the axis, we'll call it as Z. Along the axis, the coordinate is Z. This is R. And along the axis, we'll say we have an azimuthal coordinate, theta. So this is naturally done in a cylindrical polar coordinates. So therefore, at any arbitrary location, remember the original jet has a radius of R0. At any arbitrary location R, at any location Z, my radius R of Z is R0 plus a perturbation. Now perturbation would have two parts. This is the amplitude of this undulation that I have introduced. The amplitude I'll call it as epsilon. Okay, epsilon has units of length times e power omega t plus ik z. Okay. The moment I know I've done a couple of things here, and let me explain each of those steps carefully. So the first step is we say small amplitude perturbations. That's the first step, which means that epsilon is much smaller than R0. Okay. The second thing that we are saying is no twist to the filament. Okay. There is no twist to the filament, which means that the base state we know is axisymmetric, but even the perturbed state is axisymmetric. So in other words, this is in line with my drawing. You can also have situations where there is a twist to the jet, and if there is a twist to the jet, you will have to introduce this e power I n theta, okay, which is missing. We saw this in the previous lecture, but in this we are ignoring that perturbation. There's no e power I n theta. Okay. I'm also saying that omega can be thought of as omega r plus I omega I. Okay, omega can be a complex number. Whereas k is real. Okay, this tells me that it's a temporal analysis. Okay. It's a temporal analysis, and if omega r is greater than 0, notice that the exponential term will keep growing in time. I have unstable case. If omega r is less than 0, I have stable jet. Okay. And omega r is equal to 0, then I have the neutral case. Okay. So we have omega is complex, k is real, and we should also remember that e power I kz is cos kz plus I sine kz. So in other words, these undulations in the z direction, z is a homogeneous direction. It goes from minus infinity to infinity. So it's a very long filament for us. Okay. In experiments, how long is long depends on what comes out of the perturbation analysis. It will tell us whether the stationary filament is a good approximation or not after we conclude the analysis. Okay. So what's the goal? Okay, I've written down e power I kz as cos kz plus I sin kz. I'm also I'm deliberately skipping writing a real part of this perturbation every time because it's assumed to be real. Okay, so what is the goal? Goal is to obtain the dispersion relation. That is, I want to find out what is the relationship between omega and k. Okay, notice that there is no other extra parameter like a Reynolds number or so on in the problem. Okay, we are also going to say that on the surface there is a surface tension gamma. Okay, so it's a stationary filament and we have surface tension gamma. So now we'll make a bunch of assumptions. Gamma is constant. The filament liquid is inviscid, which means that viscosity plays no role at all. The outside gas is passive. What it means is that it not only of course has viscosity 0, but I also don't need to worry about solving for the velocity field, the perturbation velocity field in the outside gas. Okay, we've already seen this case, but let me write it down. There is no swirl, that is no flow in the azimuthal direction. Okay, and viscous forces are neglected. So now that we have all of this, all these assumptions or constraints laid out, let's write down the governing equations. The coordinate system that we've chosen is the cylindrical polar coordinates. So naturally we have to write down the equations in the cylindrical polar coordinates. So I'll quickly write it down. The continuity equation then I have the R momentum equation, then I have the theta momentum equation, and finally the Z momentum equation, the axial momentum equation. So these are all my equations, right? So what kind of equations are these? These are non-linear, non-axis symmetric, partial differential equations. Correct? Non-linear, non-axis symmetric, right? So let's basically reduce this to a set of simplified governing equations. Our base state is axis symmetric. Our perturbations are also axis symmetric. So I'll call them as reduced axis symmetric, reduced governing equations. Okay. So why is this? Let me write this down. Base state and perturbations are axis symmetric, right? So let's get rid of all terms which are like del by del theta terms. Okay, and there is no u theta at all, so the entire u theta equation disappears. So let's write down this equation: del u r by del r plus u r by r. Then I don't have the next term. Finally I have del u z by del z is 0. I forgot to mention that u r, u theta, u z are velocity components. These are total velocity components in r theta z. Okay, these are total velocity, so no perturbation. This includes the base state and the perturbation. Okay, but anyway, the base state in this case is trivially 0. Okay, so these happen to be the you can think of them as the perturbations themselves. Okay, the UR equation then I don't have u theta. I have uz del ur by del z will be minus 1 by rho del p by del r, and finally I have the z equation So what kind of equations are these? These are non-linear axis symmetric equations. So I went from non-linear non-axis symmetric equations to non-linear axis symmetric equations. Okay. Since there is no flow in the base state, the velocities ur, uz are themselves the perturbation velocities. Okay. Otherwise I would have had to, I'll write a step and I'll erase it. Otherwise I would have to write something like ur is equal to some base state u r plus a perturbation ur prime. But the base state ur is 0, so therefore this term is 0 and ur prime are the same. So there's no point in retaining the base state. Creating another variable for the perturbations. Okay. We also said that if the perturbation amplitude is small, that is epsilon is much smaller than r naught, then the perturbation velocity inside the filament will also be small. Right? Because the perturbations of the radius are small, you would expect the velocity that is subsequently generated is small. Okay. So for small velocities, quadratic terms, which are terms which involve product of velocities, can be neglected. Let's look at what are the quadratic terms in the velocities. If you look at this equation, there are several of them. This is a quadratic term in velocities, ur and its derivative. This is uz and derivative of ur with z, ur with uz derivative, and finally these terms. All these terms, these four terms here are small. Box terms are small and can be neglected. Okay, they can be neglected because these are perturbations and product of perturbations are small. Okay, so now what do we have now? Now we get simplified governing equations. What are the simplified governing equations? The continuity equation remains as it is from the previous step. Several terms drop out in the momentum equation. So if you look at the R momentum equation, you have the time derivative and only the pressure term on the right hand side. That's the term, right? And the same is true for the axial momentum equation. Del Z. Okay. So what kind of equations are these? These are linear axisymmetric partial differential equations. Okay. So let's basically quickly recap what we have seen so far. We started with a thinning filament. We then moved to a filament which is moving down with a constant velocity because its radius was constant. Then you can use a Galilean transformation and reduce it to a stationary filament. We looked at what kind of undulations are possible in the stationary filament, and we analyzed the case for a varicose mode. So we introduce a perturbation in the normal mode form on the base state. We haven't used the normal mode form yet. Okay, this is only to say I could have easily written this term as r of z comma t is r naught plus some r prime, where r prime is some perturbation. Okay, but since we are anyway anticipating that we will use a normal mode form, we might as well write it down. The perturbation amplitude is given by the value of this epsilon, and we said epsilon is very small. So it's a good idea to highlight that. So for us, epsilon is very small. Okay. Omega for us is a growth rate. It's a complex growth rate. If omega, real part of omega is positive, then we have an unstable scenario. And if the real part of omega is less than 0, we have a stable scenario. Okay. And the goal is to obtain the dispersion relation. That is the relation between omega and k. Several assumptions are made. We assume that the system is inviscid. The outside gas is passive. There is no swirl or twist, right? And we wrote down the governing equations, starting with the first equations are the Euler equations. These are inviscid Navier-Stokes equations in the cylindrical polar coordinates. They're non-linear, non-axisymmetric equations. All possibilities except that viscous terms are not important. I also said gravity is not important, therefore I have no body force terms here. Then we reduce them into a system of non-linear axisymmetric equations. And if perturbations are small, their product of perturbations would be even smaller and can be ignored. So what we now get is a linearized system of equations, a linear axisymmetric set of partial differential equations. What we will now do next is to introduce the normal mode form and simplify this analysis. But we'll take it up in the next lecture. Thank you.